Hello, welcome to my talk. We're talking about computational modeling of transit timing variations. I'm going to split this up into three parts. So simulating TTVs, analytical approximations of these. Heidi, sorry, I'm duplicating a lot of what you said here. And also fitting those models to determine the parameters through optimization methods. So a lot of the computational methods I'm talking about will be more abstract rather than exact code examples. But if you really want to, I'm sure you could figure it out if you spend days or weeks on it. Anyway, I'm Jack. About a year and a half ago, I graduated from Portsmouth University on my astronomy master's, basically doing this for it. Steve Futcher was my supervisor. He's in this course somewhere. And since then, I've been a Python programmer for Canonical and the Metal as a Service team. I picked one programming language and stuck with it for ages. So simulating TTV signals, specifically with Python, because that's my strength. So the first thing you need to do is simulate the exoplanetary system. You need to then compute the times of those exoplanetary transits and then determine the variation from this idealized system, where we use idealized loosely to just mean sort of perfect Keplerian orbits without any extra effects. And then as our models become more complex and more sophisticated, we can add in extra effects that we subtract in this ideal system, which often just means without the perturbers we're not interested in. Notable mentions are things like TTV fast. We're not going to be talking about that for two reasons. The serious reason is we want a lot of fine-grained control over our simulation, and TTV fast kind of hides a lot of that. The less serious reason is I'm a Python programmer, so fast computation scares me. So how do you simulate a system? Well, you need Newton's laws of gravitation. Up there on the left is the vector form, which might be less familiar, but it's still the same laws. You then run those through an iterative solver. So on the top right there is the fourth order Runge-Kutta or Runge-Kutta. I don't actually know how to pronounce that. That will essentially take your current state, run it through 4 different differential forms to determine the next state, and so on and so forth. So it's an iterative method. So that obviously will take a lot of computational time. If you want to figure out the state in 30 seconds, you'll have to do 30 time steps if you're iterating every second. So we need to have some way of speeding this up. So the 2 points I want to put on are CPU and GPU instancing. If you have a lot of very simple equations, you can say to your GPU, hey, go and work this out. And if your GPU has, say, 30,000 cores, you can do 30,000 computations in parallel, which is a massive speed up. In the computational world, we normally call this multiprocessing or instancing. It's basically just splitting this work over a bunch of smaller tasks and handing it off to specialized hardware. The other one, which is the image on the bottom left, is a Barnes hut, which is often called an octotree or a quad tree, depending on the dimensionality of your system. Essentially, because gravitation is quite weak over long distances, you can approximate many gravitating bodies far away as a single gravitating body far away. So you divide space into octets or cubes, and if you are far away from this cube, you treat it as a single point mass. So that means you have to iterate over fewer bodies, because of course in an n-body simulation, you have to solve Newton's laws for every single body, every single time you want to iterate, which is slow. So doing this can reduce computational complexity a lot. And it means you can have real-time n-body simulation of thousands of particles, whereas the naive approach using Newton's laws is maybe 2 or 3 bodies at real time, possibly 5 to 10, depending on how clean your code is. Mine's often not. And the other thing is community libraries. Python is huge and very well supported in the open source community. So rather than programming all of this naively from scratch, we can use things like Rebound and the Rebound expansion package, ReboundX, which is on the bottom right. I've got a short snippet that will create a rebound simulation and introduce the effects of general relativity, which is the other reason we're not using TTV fast in this example. We can add these extra effects really simply and integrate over time steps and add all of these extra effects. So great, we have a simulation, we can generate arbitrary systems and all of the motions. How do you get transit times out of that? Well, a first approach is just simply look for any point in the simulation where your planet's position and your star's position are aligned with the axis pointing at your observer. Now, in the real world, we don't have, defined spatial axes because Einstein didn't like that. Simplification. But in the computational world, we can just align, say, the y-axis of our simulation with where we're observing from. So that's fine. Now, it's fairly easy to see that this might be a naive example. As we know, the barycenter of the system, or the center of mass, is where our simulation is actually pointing at, and that's where all of our planets will be orbiting about. Whereas in our real observations, we're pointing at the star, and these two things are not always aligned. But I'm going to show a quick counterexample as to why this doesn't really matter. And also, trigonometry is a lot more computationally expensive than just comparing two variables. So there isn't really a lot of point in doing this. So Proxima Centauri is 4.21 light years away. It's the closest star to us. And Jupiter can offset the sun's position from the barycenter of the solar system by about 1 solar radius. Now, 1 solar radius over 4.21 light years is about 1/1,000,000th of a degree. Now, 1/1,000,000th of a degree over Earth's orbital distance is 2.61 kilometers. The Earth travels at 30 kilometers per second, so that's not even a tenth of a second's difference in your transit time using this direct line of sight versus the much more computationally expensive trigonometry. And because trigonometry, and the further away you are, the smaller this angle gets, the smaller this error is. So even the closest star to us, it's negligible, but computationally, it's not negligible. So we have to be aware what both the precision and the bounds of our computation are, because if we're wanting to solve for many transit systems, we need to be aware of this, even though I just said speed scares me as a Python dev. So I pointed out optimization there. This is another point. When we're solving for our system, we're integrating over certain steps. Now, we're only interested in when our transiting planet is in front of the star. So we can take variable time steps. If the planet is very near to transiting, we can integrate, say, a second or two in advance. If the planet is far away from the star, from our point of view, then we can integrate forward, say, an hour or a day, depending on the orbital period of the planet in question. So that's a way to speed up. And another point of using something like rebound is its engine or solver. The literature sort of mixes between the two different words. Has a variable time step built in where it will maintain a certain level of precision and use the largest time step that maintains that. So we get a nice speed up for free just by using this and being aware of the limits of our simulation. So then how do you get TTV from that? Well, I'm going to skip past this because that's what a lot of people are talking about today. But we take this simulation of our system without any of the perturbing planets. We run it, get all of the transit times. Then we run a second simulation with all of the perturbing planets on top. Say you might have 2 planets interior to the planet we're observing. And you take the transit times of your unperturbed and your transit times of your perturbed, and you subtract them from each other. And hey, there's TTV right at the end. A slight optimization here, matrix subtraction. If you're using Python and NumPy, it's a lot faster to take an array of values and subtract them using C libraries rather than subtracting them element-wise, but you're talking on the order of microseconds for each of these things. So it's not really mattering now, but again, we want to think about the optimizations whenever we're writing code, because this has the possibility of being run on a lot more expensive hardware that's a lot more expensive per CPU clock time. So it's just a good thing to be aware of. So that's it. We can generate arbitrary TTV signals for any arbitrary system. How are we going to actually determine whether any planet has TTV residuals? So we need to have models for this variation, and there are 2 kinds, the ones we're interested in and the one we're not. So the ones we're not, apsidal precession in GR, Roger mentioned that at the beginning, it will cause the signal to vary over time without there being any other planets in the system. And also tidal decay, as the planet is evolving over time, it will spiral into the star or spiral outwards depending on the rotation rates, and that will also cause the transit times to vary. Not by a lot over small timescales, but it is something that we need to be aware of because all of these other effects will come into play, especially the more accurate our simulation is. The things we are interested, however, are barycenter shifting. You can do that using simple Keplerian analysis. If you assume each planet is completely independent and non-interacting, and you solve the equations of motion, you'll see that the star and the planet will orbit about their common barycenter. And if you take this difference between the star and the barycenter and sum that up for every single planet in the system, you get a decent, if naive, first approximation for how the barycenter of the system will evolve over time. And if you know the orbital velocity of the transiting planet you're interested in, well, time is, we all know Suvat, and you can determine transit variations from this relatively naive, if simple, computationally simple, that is, barycenter shift. And that is on the top left. And if you include other orbital characteristics like eccentricity and true anomalies of the planets being different from what you'd expect on the right-hand side, you get the slightly less friendly equation. Now, we came up with this model by assuming that planets only interact with the star, which I'm sure we can all agree is not perfectly correct to the real world. So you can do another model derivation by assuming that in the bottom left there, that a planet's equations of motions are essentially standard Keplerian plus some perturbative effect, which is a lot of what NASA does when it wants to simulate spacecraft flying around in the solar system. And if you take this Jacobian, it's called, and figure out all of the variations over time, then you end up with this very unfriendly bottom right equation that has a lot of terms, and I will not stake any money it's correct, but I'm hoping it is. So you have two analytical models for TTV, one more complex, one less complex, and you can perform the same derivation to get different analytical models. And then you need to have them in code form, because remember, we're doing a lot of computational modeling. So the thing to note as well is we're wanting to work with arbitrary systems. They could have 3 planets, they could have 7. So we need to formulate our code in such a way that it takes both the time steps we're interested in and any set of bodies we're interested in. So that is on the right-hand side, that is just a code snippet, an example. It's a bit messy, I wrote it over a year ago. And on the top right is a simulated transit timing variation for a planet that I will show the example system a bit later on. And we can see that the TTV is visible, it jumps around a bit. Underneath that is what one of the models output for exactly the same TTV times. And you can see that while it is approximately correct for each of the discretized transit times, it has a continuous domain. And that's important for a few reasons. First of all, if the model is continuous, it's differentiable, which is very important later. But also, it actually has some physical meaning. Of course, on Earth, we have a single vantage point. We can't change that at the moment. So we will only see transits every single time it transits. But if you take the 7.25 transit time, what does that mean? Well, it's the transit timing variation you would expect if you were observing the star 90 degrees apart from Earth's orbit. So what this continuous domain tells us, it's not just useful information for our model being differentiable, it also shows us what the TTV would look like from different vantage points, which is very helpful. Also, we can see in the model there, this system has 2 perturbing planets, a short period and a long period. And we can see that the model has this longer wavelength and also these much smaller oscillations due to those different planets. That's a very nice sanity check that our model is producing the sort of behavior we're expecting. And it's very good to just have these sort of checkpoint parts in your code, in your program, but also just in any method you're using to make sure, hey, is what I'm doing making sense? Is it giving me the results I want? And is there some sort of actual, how do I say, I've forgotten. Is there some meaning that I can derive from this that is matching what I'm expecting? So we have our models, we have our system, we need to mush them together. So we do this through parameter optimization, and this is where our favorite friend SciPy comes to the rescue. This is a Python package that does a lot of scientific computing and a lot of statistical computing. So the first step is we take what's called a wide global optimizer. I'm specifically using dual annealing in this case. So essentially, if you have a model that has a very wide domain of parameters it can take, you'll look for a global optimizer that will stochastically cover all of this boundary region to determine what is the best fit, or I suppose the more statistical speak would be the minimal or maximal likelihood. Because this is stochastic, it can't get you exactly the global minima or global maxima. They're basically the same, just one has a minus sign. So you need to then do a second pass, and we use a narrow local optimizer such as BFGS, which I believe is Breeden, Fletcher, Goldfarb, Shano. It's basically gradient descent. So if you have your function that you're trying to optimize and you take its derivative, you can search for parameters in a small sweep around it, and the derivative will change, and where the derivative changes the most is the direction you want to go. So this is where having a differentiable model helps. So that will take your global approximately correct value and narrow it down into your local actually correct model. So this gives you the parameters that best fit your system, which is great. But then we bring in another Python package, MC, which does Monte Carlo Markov chain searching, to take your parameters and does random permutations of all of these to determine the boundary conditions. So what are the error bars on my parameters? How much larger can I make the semi-major axis from one of my perturbers for it to give approximately the same TTV signal? And because we're working with real observations rather than simulation, we have error bars and everything. So it's really useful to be able to say, hey, what are the actual parameters within the observational limits? So there we go. We have models, we have TTV signals, and we have ways of fitting them to each other. So you just need to combine it into a single cohesive whole. The steps for this will vary depending on the exact implementation. This is just how I did it. So in light blue is sort of the information you bring in. So what does the system look like as far as we know? What are the ephemerides of all of your transits, of all of your planets? What is the mid-transit data? Because we're trying to search for transit timing variations. In light green is all of the steps we've spoken about. You need to determine the TTVs, you need to fit each of the models to the data, you need to find all of the fit parameters. And then in purple is the output. And there is a small self-promotion there for some of my code at the bottom. So the example output, it's scary. On the right-hand side, we have all of the models with all of the fit parameters, and you can see that each of them have different outputs that show the different characteristics of all of those models, and some of them fit the black data points really well, some of them don't, but that's to be expected. That's why we have multiple models. And on the top left is the example system I mentioned earlier. We can see that there's a red exterior planet, which is the one we're observing for TTV, and there are two interior planets that we're looking at as perturbers. Underneath that, on the right-hand side, is the second best fit. So after I did this, it took about 3 to 4 hours on my CPU to fit each model to this dataset for, I think it was 200 years of TTVs, which is way more than any real planet we have, which is another thing to be aware of. In simulation, we can go arbitrarily far into the future. In the real world, we're limited by the observations we have, which is 20 years at best for a lot of planets. But yes, underneath it, on the right-hand side, is the second best fit. And we can see that it's determined there were 2 planets in the system, and the interior most perturber was about where it is. but the exterior-most perturber was on a much broader orbit. But looking in the model, that's because it was lower mass. On the right-hand side, we can see it's only found a single perturber. And this is where one of our problems come in. With models like these, it's very easy to assume that because your model fits, it must be true. But in this case, a lot of models that fit can find sort of a single ghost planet. If you have two perturbers, it's a lot easier to falsely fit a single planet that's sort of the average of the two and get stronger TTV signals within the bounds of your model. But also, if one of your planets, one of your perturbing planets, is a lot more massive than the others, you'll find the TTV signal is dominated by that. So you'll have a lot harder of a time pulling out the signals from your weaker perturbers, even if they are there, and causing TTV. So this is another thing to be aware of in your model, and it's really just showing you need to be aware of where are the boundaries of all of your analytical approximations, as Heidi mentioned, and also what is the boundary of the precision on my computation. If you're integrating into time steps of an hour, you might be losing out on very fine-grained details that will add, say, another perturber to your system. You can kind of fix that. Oh, I should probably mention the bottom left, that's a very scary plot. This is where our MCMC sampling comes in. And if you don't like statistics, this is the scary bit, because this is where we start talking about words like Bayesian sampling and Gaussian distributions, which are scary, I would know. But yeah, one way to fix this is you fit for a single perturber, you assume that perturber exists, and then you fit for a second perturber, and so on and so forth. But you have decreasing confidence that each perturber exists because you've assumed that your previous fit was correct. This is just another way of finding more planets, but you have to be aware of what are the bounds of my simulation, what are the bounds of my assumptions, what are the bounds of my models, and so on. So we have code, we have an output, and that is it. I hope that was okay. And are there any questions for the floor?
Thank you, Jack.
Thank you, Jack.
Yeah, it's fascinating and yeah, very. I know from coding myself in Python how yeah, you got to kind of, there's lots of different elements you've got to balance to get things working as you need them to.
Oh, 100%. I write spaghetti code at work all the time.
I think there was one question on the chat, Andy, wasn't there?
Just going to, yeah, so we have from Siegfried, have you used global optimization methods like differential evolution? And there's a few parts to this question. What are the advantages of dual annealing SciPy? And do you have code available on GitHub? I can go over each one of those in turn if that's easier.
I can answer all three in like 2 or 3 sentences. I have used global optimizations like differential evolution. SciPy ships with 5 different global optimizations by default, and I used all 5 of them, but I only mentioned dual annealing because it's the one I've had the most success with. The advantage of that is I've had more success. It tends to run faster and give more precise outputs, or at least on my hardware. And all of the code is available on GitHub. I can link it if people want. I'm currently in the process of reworking it in my spare time, but that will be soon. So yeah, my original code is definitely there.
And we have one from Hannah, which is the representation of this data is very visually appealing and understandable. Thank you. And then Daniela, that was an amazing and very interesting presentation. And Paul Dooley, have you considered using a compiled language rather than Python to speed up the processing?
So I don't really have a lot of experience with languages other than Python. I did a bit of Fortran in my undergrad, and I've been exposed to a little bit of C in my job, but not nearly enough to perform any of this computation in it. I know a few people that are more familiar with things like Fortran that could probably do it, and I would see the speed up as very beneficial if this were to be transferred from more of a hobbyist thing to an actual real pipeline implementation for space telescopes. So absolutely go for it. The computational speed up is, Python versus Fortran, I think, is 10,000 times slower for the same thing. Also, Python comes with certain ways of speeding up. For example, the number package, I believe it speeds up Python, numerical Python tasks by about 1,000-fold. But I haven't done that yet. I'm welcome to contributions if anyone wants to, but this is definitely something to bear in mind if you're going to use this in an actual academic standing rather than just hobbyist, essentially. Oh, also
Actually,
Rust. That's a good point. I saw that.
Yeah. Actually, I can add a bit on that as well. If you're using things like NumPy, then it has a significant increase on the speed. And I think that's because a lot of it is kind of under the hood done in C libraries.
Yeah, so NumPy kind of, it takes all of the base C derivatives and attaches just a Python API into it. So when you execute a NumPy array, you're not actually doing anything in Python. You're just giving it to the CPU in an exact vector form that it can do very fast computation in, and it will throw it back out.
Having a look, there's a few comments relating to this. From Siegfried it is possible to use F2Py and Cython to wrap C and Fortran code into Python modules. And also Paul Dooley, as I've used Rust for simulation work at about a factor of times 100 speed up, also times 1,000 speed up. I would also say in my own work, which I've sort of used Python NumPy, and I've got a supervisor who uses Fortran. And actually, when using NumPy, you can get similar speeds to Fortran if it's kind of done in a nice kind of efficient coding way.